Welcome to the Explainer. If you're deep into electrical engineering or just kind of fascinated by the hidden magic powering literally everything around us, yeah, like that smartphone you're probably holding right now, you are the exact right place. Today, we're taking a foundational journey into the language of circuits. We're going to take these core principles and just break them down so they make perfect, intuitive sense. No stress, just logic. So, let's jump right in. Have you ever stared down a really complex circuit board, or maybe a dense schematic that's just packed with lines, squiggles, numbers, and you just felt, well, a little overwhelmed? It honestly looks like a completely different language, doesn't it? Well, that's because it actually is. And, just like learning any new language, it's super intimidating if you try to read a whole novel before you've even learned your ABCs. But here's the secret. Every single language is built on a very simple alphabet. And by the end of this explainer, that intimidating schematic is going to start looking a whole lot more like basic arithmetic. All right, let's start with literally the very first letter in our electrical alphabet, charge. It's basically defined as the characteristic property of particles. So protons, they've got a positive charge. Electrons, negative. And neutrons, well, like the name implies, they're totally neutral, no charge. And the unit we use to measure all of this is the coulomb. To kind of picture this in your head, just imagine a single unit of charge as a single drop of water, just resting in a massive network of pipes. It is the absolute fundamental building block of literally everything we're about to talk about. Now, obviously, one single drop of water just sitting there perfectly still, it doesn't really do much of anything. But what happens when millions of those tiny drops start rushing together in the exact same direction? Well, that brings us to electric current. Current is simply the rate of flow of that electric charge. So if charges are a single drop of water, current is the rushing river inside the wire. We measure this flow in amperes or amps, which basically tells us exactly how many coulombs of charge are flying past a specific point in one single second. It's all about movement. Okay, so here's the next really crucial question. What actually makes that river flow in the first place? I mean, real water needs gravity or a physical pump to move through a system, right? Well, in our electrical language, that essential pump is what we call the electromotive force, or EMF. It's defined as the actual force that causes a current of electricity to flow. It's that gentle or, sometimes not so gentle push that gets all those resting drops of charge moving along their path. Think about the battery inside your laptop. Without its EMF providing that initial push, the current just stands completely still. So we've got the push and we've got the flow. Now we need to look at the actual cast of characters that interact with all that flow. And we can neatly divide every component of an electrical network into two main camps: active elements and passive elements. Active elements, they're the ones doing the heavy lifting. They literally supply energy to the circuit. Think of things like a battery or a voltage source. They're the providers. Passive elements, on the flip side, are the receivers. They don't supply energy, instead they either dissipate it, kind of like the heat radiating off the coils in your toaster, or they temporarily store it away for later, like a tiny little electrical water tower. And honestly, beneath all the apparent chaos and complexity of a messy circuit board, there is just this beautifully organized family tree. The whole ecosystem splits so cleanly. You've got active elements on one side, which break down into your voltage and current sources, and then passive elements over on the other side. It's a great reminder that underneath all those tangled wires, there is a highly logical, deeply structured relationship of components, all just working together to power our devices. Now, if we zoom in on that passive family, there are three fundamental characters you're going to run into in almost every single circuit. First up is the resistor, which we symbolize with an R, and its whole job is basically just to dissipate energy. Then we have the inductor, L, and the capacitor, C. Both the inductor and the capacitor act like storage units. They just hold on to energy in slightly different ways so the circuit can use it later. And that's really it. Just those three simple components. They form the entire foundation of nearly all passive network interactions.
Okay, I know what you're thinking. Looking at differential equations for inductance and capacitance at time zero might cause a momentary spike in your heart rate. But let's take a breath and look at what the underlying principles are actually trying to say here. They state that inductance current cannot change suddenly, and capacitance voltage cannot change suddenly. That's it. All these intimidating math equations are doing is telling you that these specific components absolutely hate sudden, jerky changes. They prefer a nice, smooth, steady transition. It's kind of like how you feel when your alarm goes off on a Monday morning, right? They just want a little time to adjust to the new reality.
All right, so now that we've met our cast of characters, we need to learn the basic rules of the road that they have to follow. Enter Kirchhoff's current law, or as we usually call it, KCL. I want you to picture a node, which is just a junction point in a circuit, as a super busy but perfectly orderly traffic intersection.
Cars are driving in from a few different roads, and they're driving out through others. KCL simply states that the total number of cars entering that intersection absolutely must perfectly equal the total number of cars leaving it. No cars are just magically disappearing into thin air.
Actually, let's break Kirchhoff's current law down into 4 incredibly simple, low-stress steps. Step 1, identify your node, just find the intersection. Step 2, add up all the current flowing into that point. Step 3, add up all the current flowing out. And step 4, just set those two numbers equal to each other. Yep, that is literally it. It just reinforces this beautiful, reliable logic that whatever energy goes in simply has to come back out. It's the ultimate rule of balance.
Now, what's really interesting here is how our perspective shifts. Instead of just staring at a single intersection, we're going to trace a path around the entire neighborhood block. And this brings us to our second major rule, Kirchhoff's voltage law, or KVL. So instead of focusing on one point, we're drawing a complete closed loop around a circuit. Imagine you're just going for a walk around the block, and you're noting every single rise and drop in elevation, or in our case, voltage, along the way, until you arrive right back exactly where you started.
And the core concept here states that the algebraic sum of voltages around a circuit must be 0. Now, I really like to frame this not as some sort of strict, scary mathematical decree, but really as a statement of perfect, balanced harmony within the electrical ecosystem. If you gain some energy from a battery, you are going to lose that exact same amount of energy pushing through the resistors and other components before you finally make it back to the start. The journey literally always balances out perfectly.
So as we start wrapping up this explainer, I really want you to remember this one thing. Complex systems are literally just simple elements obeying basic rules. Seriously, you do not need to memorize every single crazy network diagram today. If you just focus on understanding the flow, knowing where the push comes from, how the current actually moves, and how the components interact to keep everything balanced, the memorization will totally come naturally later. Understanding the logic is just so much more valuable than rote memorization. We've walked through the fundamental alphabet, the basic grammar, and the core rules of this invisible world. You understand the push of EMF, the flow of current, the providers, the receivers, and the beautiful harmony of Kirchhoff's laws keeping it all in check. You are absolutely no longer looking at an intimidating alien language. So I want to leave you with this thought as you continue on your engineering journey. Now that you actually know the alphabet, what kind of energy are you going to guide next? Thanks so much for joining me on this explainer. Keep learning and keep flowing.